Okay, so let us start with this topic. The course content, as you can see on the screen. Okay, so this talks about several topics which I left over in the last uh, class yesterday. So that was multiple sources, basically the MLI, multi-level inverter, and cascaded multi-level inverter, which is of multiple sources. And then we'll be talking about today's main topic, that is the neutral point voltage variations. And in the neutral point voltage variations, we'll try to understand why, first of all, the neutral point voltage variation such an essential problem to solve. And particularly single source based approach, this is the problem. And then we'll try to take some example of three level inverter, try to understand the neutral point balancing issues and for different loading and power factor conditions. Okay, and then not only that, we try to see, look at the effects of load imbalance and nonlinearity in the neutral point voltage balancing issues. And then we'll be discussing different solutions, state of the art PWM solutions available in the literature. We'll go one by one of each one of those, probably all of them, all of the important ones available in the literatures. And those discussion, after the discussions, will show you some of the future trends and where the active research is going on last 3 4 years. So that way I'll finish my complete my discussion today. So I expect that you will get some idea and some encouragement to work further on this area as a researcher. So keeping those things in mind, I'll start begin my first content, and that is of cascaded MLI, edge bridge based MLI. Okay, so as you can see, some of you are already aware of it. So just I'll just show you the salient points of cascaded MLIs. Okay, so this it is formed by as you can see here, for this particular 5 level cascaded edge bridge inverter, you have two edge bridge units corresponding to a particular phase. So each phase has two edge bridge unit and they are connected in cascaded manner. That's why the term has come, cascaded edge bridge. So now when you have the two cascaded separate cell H1 and H2, so these need to be provided with a supply, a DC supply, and this is supply of H1 and this is supply of H2. They are actually isolated, so they cannot have a common ground. Okay, they don't have a common reference point. So these are how you may be wondering that how these sources can be formed. This E and E, if you are talking about a particular phase A here. So these actually can be either can be a PV source which is naturally available, isolated by its nature, a particular PV source, a PV panel, and this another for the next cell, next module, you can have different PV cell, okay, PV panel. So by inherently they are isolated in nature, but if you want to use for some other purpose, not only for PV application, so there you have to have a transformer isolated in your inputs, and then you have to rectify that, and then so that you get the required DC voltage E, and that so as they are actually separated by transformer, so then they are inherently isolated to each other, although the input supply are the same. Okay, so that way, that is the major concern. It cannot work if there is a common reference of between these two sources. So similarly for other phase also. So see, if you look at the three phase MLI structure, so then all these six supplies need to be isolated. So generally it is not advisable to for actually using a transformer, but in some PV applications these are actually very good. These are naturally isolated supplies you will be getting. So that is the very important point. Then we come to the operation of five level. So basically, why these five levels are coming? Because if you look at a particular edge bridge unit, so each particular edge bridge unit can provide you three distinct level with respect to this E. So one is the plus E and minus E and the zero level. Okay, so we'll be coming to know that how this we'll be seeing very shortly how these levels are you can achieve for a particular module. Okay, HBS module. And then individually this is giving three levels, and then similarly the bottom one also individually giving three levels. So in out of these 3 plus 3 6, one level will be common because they are connected in cascaded manner, so there has to be a common level. So you will be getting 6 minus 1 5 levels. So now you can, if you wish, if you can increase this module number of modules and in a cascaded manner. So there must be whatever the number. Finally, there has to be a common reference point when you are supplying to industrial loads or to grid. So there at the other end, the end capital N is written that there is a common reference point. With respect to that, you are actually generating these three voltages A, B, and C. These are phase voltages. Okay, so like that you can increase the number of levels, but at the cost of something, at the cost of more number of switches, more number of resources in terms of supplies. Okay, so each leg has two possible switching states to avoid DC-link short circuits. Okay, so there are two possible switching states. Either you switch on S for a particular module, this one, so S11 or S31, if you both are turned on, so through this top DC link they can get sorted. Okay, so or if you turn on both S41 and S21, then through this DC link, this point A, these 2 points or output points, they may get sorted. So you can avoid sorting the DC source, but you can sort these two terminal without sorting the DC source. So that is what it is said. It is saying here, and there are four different switching states, and these are actually shown here in the next slide. So you can see here clearly. So if you want to get a particular level, so this is not a PWM kind of switching, so this is just a very low frequency switching. Okay, so just to give you some idea how the levels are coming by switching different devices. So here if you switch on S1 and S4, so this entire this VDC, earlier it was depicted as E, but the same, both are same. This VDC is coming at the output terminals across these output terminals. So this is plus VDC you are getting if you turn on S1 and S4, and then you can turn on S1 and S2, then you will get this zero level. Okay, so that zero level can also be achieved if you switch on S3 and S4, but in this particular case you are more interested to switch on S1 and S2 combination, because earlier it was okay. So that depends on you actually how you want to get it. Okay, so if you could have switched S3 and S4 also, that's not a problem. So you have two actually redundancies of this zero to in order to get the zero level, and in order to get the negative voltage. So negative voltage you have to switch on S2 and S3, S2 and S3, so that between these two terminal you are getting the negative VDC. So that is what is shown in the bold line. And so this is not the PWM, but in order to get the PWM output of three levels, so you have to use the unipolar PWM modulation technique, and that I'm leaving to you. Some of you may be knowing, and some of you may explore more on the unipolar PWM techniques, where you can get a PWM output in three levels. Okay, so this is about the cascaded edge bridge MLI. So the advantage, another advantage of this cascaded MLI is that it is actually a modular in structure, right? Sometimes the industry love this kind of structure because a single unit is getting repeated and the next block. Okay, and if you want to add them, if you want to increase the level, so you simply have to add them, you have to add another similar blocks, so that blocks are actually there is a symmetry. So this block, first block, second block, and third, all these six blocks, they are of same nature, same VDC value, and rating of the switches are the same. So they are modular in structure, and they are easily scalable to any high power level. If you want to increase the power level by means of increasing the voltage level, so you can easily put them, or put more number of this kind of HB cells in cascaded manner. So that is the advantage. Also they have some more fault tolerant of operation capability. So if something is some is a problem in the particular cell, you just sort these two terminal to bypass a particular manually, or some physical connection contactor, you sort it, so that any problem you can isolate this block from your circuit, main circuit, and you can still run this whole circuit in a low power level. Okay, so that is also possible. So for those reasons, this kind of structures are very popular. But only problem is that you need to arrange many number of sources, isolated sources. Okay, so with this introduction, so if we try to summarize what is the merits. So modularity of the structure, enable fault tolerant operation. All semiconductors have to block. Yeah, these are the same. And they are not different in nature, so there are symmetry in the characteristics of the semiconductors. So if you want to buy the semiconductors for your inverter in a bulk amount, so if they are in the same rating, so you will get a lower price quote for your semiconductor purchase. So that is the another advantage. And high voltage operation without switching device in series. Yeah, so this is the basic advantage of any multi-level inverter. And the drawbacks, yeah, as I said earlier, each bridge inverter needs an isolated DC source. But sometimes this drawback is not a drawback itself, because in PV applications, isolated DC sources are available. So, and another point is that high component count, that is really a problem. So we have to deal with high component count when you are dealing with high component count. So more failure rates in the inverter structure is possible. Okay, so that is all about this multiple source based multi-level converter. And now we'll come to the next topic, and this is the main topic, today's main topic. We'll spending a little bit of time on this particular topic, and I hope you pay your attention for this discussion. Rest of this part of the discussion very attentively you will be listening. Otherwise you will actually lose the track. So so you have to understand each one of these steps in order to follow next part. So we'll be trying to understand the neutral point variation in single source based converter. So yesterday we have discussed a lot about three level converters and neutral point NPC structures, and then flying capacitor structure. Even the neutral point structures, neutral point clamp based MLIs, they have different varieties like NPC structure, and then T type NPC. So those three-level converters, T-type NPCs are there. So there are different varieties are available, but the common thing for all of these, actually they are using a single source. And sometimes this is a very attractive feature, to use a single source than using multiple sources. So many application, and the single source is preferred, and particularly in a back-to-back operation, where in a particular drives application, or in an electric vehicle, or any kind of application where you need to get back the power, the regenerative power back to the source, then it is much easy if you have a single source. So this draws a lot of attention, but the problem comes if you go more than two level. Okay, so why the problem comes, not for flying capacitor but for other NPC structure where they use the neutral point, the middle point of the source. Okay, so where you can see here in this middle picture, so you have just a second, I want to use this laser. Yeah, so in this middle picture you can see, so here you have a single source, but in order to get the midpoint you have to have two capacitor midpoint, so that can be utilized as the middle midpoint potential. Okay, and when any phase out of A, B or C, so any phase is connected to this midpoint, so there is a current is flowing through this midpoint connection, and this current is actually your load current. Okay, so when you are talking about your medium power application, so this load current is not very small one, right? So this load current can go few hundred of amperes, and up to that level it can go. So when that kind of huge current is passing through this midpoint, and that is actually also has to pass through these capacitors. So for simplicity you can assume when some of the load current is passing through this neutral point, so this load current is getting shared equally by these two capacitor. Okay, so then you can understand, suppose if you 100 amps are flowing, so 50 amps and 50 amps are flowing here, so this top one, this 50 amps is charging this upper capacitor, whereas the bottom one, this 50 amps is discharging the bottom capacitor. So as a result, so you can see there is increase of the voltage, and for the same reason there is a decrease in the voltage for the bottom one. So you can see one is increasing and another is decreasing, whereas the total voltage remain the same, that is actually held by the source VDC, but actually the deviation is happening between, so they are no longer equal. So in ideal condition the top one should retain VDC by 2 and the bottom one should retain VDC by 2, but in some ideal and non-ideal condition, not non-ideal condition but any conditions wherever this switch is getting connected, any phase is getting connected to the neutral point, so then they are trying to deviate from each other. Okay, so that's why we say that neutral point is no longer a zero potential, it is sitting at some other places. Okay, so how it can happen, so if you look at this switching table, if you look at the for NPC structure, so if you look at the switching table, for in order to get plus VDC by 2 at the output level, so and if you refer this right side switches, then this S1 and S2 are the top two switches. S1 is SA1, SA2, SA3 and SA4, like that. So when you want to get a particular voltage VDC by 2 plus VDC by 2, these then top two switches are on. So then there is no interference of there is no current is actually flowing through this neutral point, so it is coming from the top bus. Okay, positive bus, and then it goes to the load. So then there is no problem, so we are actually have listed down here, so neutral point due to a phase for plus VDC by 2 is 0. Okay, and similarly for getting minus VDC by 2 also you won't see any problem in the neutral, there is no current is flowing through the midpoint, so for that also you get 0. But the problem come when you try to achieve this midpoint volt, you want to get this voltage at the terminal of the pole. Okay, so then you can have this combination S1 these two switches are on, the midpoint switches are on, so either of this direction of the current, whether current is going this way outward or current is coming inward, so irrespective of the direction of the current, it gets a path. Okay, through this combination of switches and these two diodes, and this is flowing either in this direction or in this opposite direction through this midpoint, and that is causing the trouble here. The midpoint, this point is no longer sitting at 0, and because these two capacitors actually trying to deviate from each other, capacitor voltages trying to deviate from each other. And from this configuration, from one example can be set. So this example in terms of vector switching, suppose as you know, if your vector is POO, actually this P depicts when the positive value, P for positive value, O for midpoint zero value, means zero potential, and there is also another state is called N. N is not shown here, but here this the status of the vector location is POO, and that vector is being applied. And when this vector is applied, then your A phase is sitting at this terminal, and other two phase B and C is sitting actually connected to this midpoint terminals. Okay, so you can see easily so basically the current, which is the current in A, that will flow through this, but B and C will be contributing to the midpoint current, because these two are actually connected through this combination of switches and these diodes, and to this midpoint connection they will be connected. So this is the kind of scenarios, vector switching. You are supposed to get a midpoint current, and that will fluctuate the voltage of the midpoint. So similarly, there are so many other vector locations which will cause these midpoint voltage fluctuations. Okay, so let us so if you understand this part, so then, okay, yeah, so then let us come to try to understand more actually uh, constructive manner. So for all the vector locations and for vector application, what how your actually neutral point can be affected. So let us before that, you have to understand the three level space vector structure. So let us try to identify different vector location of three level space of any three level NPC inverters. What are the different space vector structure? So here you can see this is the midpoint. So when either all the switches are connected to the top bus, or all the switches connected to the midpoint or the bottom bus, okay, negative terminal of the bus. So then this is depicted as a zero vector location. So it has three redundancies. We use the term redundancy because this particular vector location can be achieved by three different manner. Okay, so these three different vectors are there, but the location, all these location of these vectors are the same. Similarly, you can see there are other vector locations for three levels. So this is actually this n. These are there are some large vectors, there are some medium vectors, and there are some small vectors. Okay, apart from these zero vectors. So these are the large vectors. If you go by the length of the vectors from the distance of the midpoint, so you can easily understand that these are the PNN and PPN and NPN and NPP and NNP and PNP. These are the large vectors. Okay, and you can easily understand the symmetry. So if this is the PNN, this has to be opposite of that. So P is opposite is N for the A phase, and N opposite is P for the B phase, and N opposite is P again for the C phase. So look, so like that you can get easily the symmetry of this whole space vector structure, whereas this particular axis is actually along the a axis, and this particular axis is along b axis, and this particular axis along c axis, assuming that a b c sequence. Okay, so these are the six actually, one, two, three, four, five, and six large vectors. Similarly, you will get medium vectors. Medium vectors are, and these are the medium vectors. Again, you will get six different location of medium vectors. One, two, three, four, five, and six. Okay, this is little lesser than this large vectors, so that's why they are called medium vectors. And small vectors, they are sitting inside, okay, this structure. So these are these locations: one, two, three, four, and five, and six. Again, there are six locations for the small vectors, but the small vectors have actually have redundancies of two redundancies for each location, or for each vector locations. So for this particular locations, there are POO and ONN. So this can be, this particular location can be achieved either by this way, by applying POO, or by applying ONN. Okay, so same vector location can be achieved. So they have a two redundant vectors for the small vectors. For each one of these they have two sets of vectors. Okay, now as you can easily understand, very without applying any mind, actually, little with applying little mind, you can easily understand that this Pn in there is no O is involved, right? And here also Ppn there is no O involved. Similarly, P and P. So all the large vectors there is no O involved. So there is no chance that your neutral when you are applying this but these vectors your neutral point current will not be flowing. Okay, so they will not be contributing to your neutral point current, and that's why they will not create any problem of any imbalance. So let us try to understand more in details by these definition, large, medium, and small vectors. Okay, so this is actually taken from one of the reference. So in that reference, it was well explained. So you can also search this reference to for get better understanding. But for simplicity, I am actually showing you. Trying to explain you more something more so that you can easily grasp the idea. So what is that? So you basically you are categorizing three classes of vectors as I said earlier. So now if you look at small vectors. Small vectors, it has two classes. One is the positive small vectors, and then one other is negative small vectors. And these two are different. And then you have the medium vectors. Okay, and we have discarded the large vectors because large vectors, as I said, it is not contributing to any neutral point fluctuations or neutral point current. But while it comes this small vectors, that is, for example, this particular location, if you look at ONN and POO, so basically they are the same vector location, but one is classified under positive, another is classified under negative. Why is it so? Because if you look at ONN, this is actually the neutral point is contributed by this application of this vector is IA. So why it is IA? Because this N in B phase and C phase they are connected to the negative rail of the bus. Okay, that means if you look at both are connected at the negative terminal of this bus B and C, but A is connected only in the middle. Okay, so that's why it's called ONN. So ONN, yeah, so A current will be directly affecting the neutral point, no other phase current. So that's why it is A. So this A can be either outward direction or inward direction, does not matter. So it is A, simply written in that term. But if you go look at POO, same vector location, here A phase is not directly contributing the current because it is connected to the positive rail of the bus, but both B and C are connected to the midpoint. When both B and C connected to the midpoint, they are contributing minus of IA. Okay, so it is indirectly. So why it is indirectly? Because this is the application where all the time instantaneously IA plus IB plus IC is equal to 0. Okay, where your load neutral point is not connected anywhere else. It is floating load neutral point. So that has to be true always. So IA plus IB plus IC is equal to 0. So if that is the equation. So IB plus IC will be always equal to minus of IA, and that is what you can see here. POO is giving you minus IA. So always these wherever this positive one is this, the other redundant vectors will be negative one. Okay. Similarly for PPO, if you look at this vector location PPO, and this is giving IC. Okay, because the C phase is connected. So the other one, other redundant of OON will be giving minus IC. So they are actually just the opposite. Okay, one is giving the positive, other one will give the negative. Okay, so that's why they are classified into two different small vectors, positive small vectors and the negative small vectors. It just a name is given. Okay, so and what about the medium vectors? Medium vectors, if you look at, so they have all the medium vectors if you list down the six medium vectors, they have only one O. Okay, either of these three phases, they have only one O. So here this O is connected to B phase, so that's why this IB is coming. Here the O is connected, C phase is connected to the midpoint, so that's why IA is coming. And here C phase is connected to the midpoint, so IC is coming. So like that you will get all this classic, all these different contribution for different medium voltage vectors. Okay, so this is the table which summarizes that when you are applying different vectors, what is the kind of effect you are going to get in terms of neutral points. So we will be talking about the small vectors. So effects of small vectors SVs on the NP voltage variation is the large vectors, as I said, and zero vectors do not affect, and zero vectors obviously do not affect. Whereas the medium vector is the main source of NP voltage imbalance, because in medium voltage you have seen that there you cannot balance, right? Because in small vectors there is a possibility to balance, because either you apply these redundancies, or you probably change over to this redundancy vector. Then one time you are getting plus IA, another time you are getting minus IA. So there is a possibility of balancing, okay, by using the same vector location. Okay, but here medium voltage vectors, there is no redundancies. Okay, they have only one vectors. So but this one vector has some particular value, so that's why it says the medium voltage main source of NP voltage imbalance makes NP voltage dependent on the load condition. And whereas small vector has the effect on NP voltage, comes in pairs. Yeah, so this comes in pairs, as I said, like this, generating same line current but with opposite direction of INP. Okay, so most of the space vector modulation based NP voltage balancing technique uses some sort of manipulation. So now these will be discussed in details, how the control technique will take place, so that this neutral point balancing can be tackled. Neutral point imbalance can be tackled. Okay, so that I'll be discussing in a later part, but let us try to continue with this. So to try to understand what are the effects, because this is the kind of table you have got, but still you need to clear some of more pictures on what are the effects when you are getting, actually you are actually supplying some load. Okay, and that some particular load have some power factor condition. So different power factor condition, what will be the effect on the neutral point fluctuations. Okay, that we are trying to understand now. If we try to understand that thing, then it will be easy to give a solution. So first we will try to understand how much is the fluctuation. So effect of medium vectors and small vectors on NP voltage variations, first we will try to understand more in details. So here, if you try to see that, if you want to synthesize this vector, you are already aware of this space vector modulation technique. So what it does, if you want to synthesize these vectors, and this vector is rotating, suppose it's anticlockwise, okay, or in ABC sequence, it is rotating in anticlockwise. So for this particular location, that means for Ts time, so actually you are giving applying three vectors, nearest vectors, right? Because the tip of this vector lies here, so it falls under this triangle. Okay, so now this, there are three vectors. One is VSO here, and VL is large vector, and one is VM vector. And here I am depicting as VSO as a small vector here. So each one of these vectors, by from volt second balance, you will get this equation. So basically duty cycle is the time it is staying at this particular location divided by the total TS time. Okay, so each one of these D term, you have a denominator, you have, it's basically a ratio. So in denominator you have TS term, that TS term can get multiplied here. So basically this equation comes from volt second balance equation. So for each one of these volt vector location, you have respective duty time. This is a ratio, which is the time indicates you are staying here in a particular location of the vector with respect to Ts time. Okay, so the time allotted for vs, the time ratio allotted for vs0 is ds0, and the time ratio allotted for vm is dm, and time ratio allotted for vl is depicted as vdl here. So finally there has to be one, because total time will be ts time. Okay, one switching cycle time. So once this thing is clear, then you can easily understand that there is a chance that you can manipulate this DSO, right? Because you cannot manipulate DM, because, and you cannot manipulate you cannot split rather DL and DM, because they have only one particular vector, nothing to switch at. So when you are applying this vector location, there is no redundancy for this location. But whereas for this, there is a two redundant vectors. One is ONN and POO. Okay, so one will be actually having giving you positive current effect, and another is giving you the negative current effect in terms of neutral point. Okay, so relative duration of positive and negative small vector pair is denoted as MSO. Okay, so you are actually bringing a term MSO which is actually varying from -1 to +1. This is just a definition. It is the definition in your hand. It is, we are trying to express in terms of MSO. Okay, so how MSO is actually playing a role? So it can vary from -1 to +1. When it is 1, so it can attain a value in between -1 and 1. It can attain a value 0 in between. So when it is -1, so that time you are giving all the time to the negative vectors. Okay, when it is 1, you are giving the time all the time for the positive small vectors. So due to ratio of the vectors VSO1, this is the positive vectors, okay, ONN is 1 plus MSO into this DSO divided by 2. So if you assume, if you MSO you are is 1 here, okay, MSO is 1 here, so that becomes DSO is become total entire DSO, it is getting the positive vector is getting entire DSO. So basically this DSO is getting splitted into two halves, right? One part you are giving to the positive vectors, another part you are giving to the negative vectors. So by introducing this term MSO, you are actually can write an equation, the duty cycle for positive vector and duty cycle for the negative vector. So for the same case study, if you see if MSO is 1, here also MSO is 1, if you put that, that becomes 0. Okay, that means then your entire time, entire duty cycle you are providing to the positive vector when MSO value is equal to 1. And when MSO value is equal to -1, then the entire time you are giving, or entire duty cycle is poised upon this VSO POO, is negative vector. Okay, so that way you can modulate, or you can change the value of MSO, so that either you can give more time on this top one or the bottom one. Okay, so the neutral point, your neutral point will be can be for this particular location. Okay, the outer small triangle, if you write like that, neutral point is dm into ib plus mso into dso into ia. So you are introducing this term intentionally. So this is a control term. Basically, you can control the ratio of MSO. This is in your hand. By controlling this MSO, you can have an effect on IN. Okay. Whereas the DM you cannot control, because DM there is no redundant vectors. Whereas the MSO, by controlling MSO by in your hand, you can control this part. So that's why it's called controllable component, whereas this is called non-controllable component. So now in the another case study where the V reference instead of sitting here, it can be for different modulation index, it can lie in this zone. Okay, so this comes under this shaded triangle. Okay, so when it comes under this shaded triangle, you are supposed to switch these three nearest vectors as from the rule of the space vector switching technique. So you can easily understand. So these three vectors will be switched, so you can easily understand the neutral point. So I'm not bothered about any other point, current flow, but I'm talking about the neutral point, how it gets affected when it's lie here. Then it has three different vectors. Okay, one is the medium vectors, and other two are the small vectors. Okay, this one I'm depicting as s naught, then the further the furthest one is depicted as vs1. So that's why you have two controllable part here. One is for MSO for the nearest one, and the furthest one is MS1, which is actually the vector location here. Okay, again you have two redundant vectors. Okay, for VS1 location, small vector location. So again you have another controllable parameter MS1 for when you are switching this particular vector location. Okay, so you can find out another expression of INP for different modulation index when it is passed through this particular zone. But for the same theta, but very interestingly, it is the same theta, but their vector length is changing. Okay, vector length is changing. And for the third one, third case, you can see when vector length is changing further down. So in this case, this one lying in this particular triangle in this shaded area, so you will be switching these three vectors including the zero vectors and two small vectors. So in the zero vector does not contribute to any neutral point, so that expression is missing, need not to be here. So other two vectors vs0 and vs0, so vs0, from vs0 ms0 is a controllable parameter, and from vs1 ms1 is a controllable parameter. As similar manner, actually ms1 can be also defined, ms1 is also in the range of -1 to 1, similar manner. So you can easily understand that there is always you will get a controllable component, so through which there is a possibility that you can control the flow of neutral point. Okay, and that control lies in this index ms1 ms naught, and in this equation also ms naught ms1 is there, and in this equation also you have ms naught. Okay, so we can summarize that steady state low frequency. So you generally observe a steady state low frequency. Generally, if you don't control this ms1 and ms not in appropriate manner, so you are supposed to get a steady state low frequency ripple in the neutral point current, and that is caused by periodic variation of duty cycle of vectors over the output line output voltage line cycle. So over a fundamental cycle, if you just observe, this is a particular location of the vector, but this vector is rotating in 360-degree angle in one fundamental cycle. So if you observe this entire location of an entire area of the waveform, then you will observe there is a pattern of neutral point and voltage ripple. Okay, and that gives rise to a low voltage low frequency ripple in the neutral point voltage. Okay, so basically, if you want to understand this entire distribution of 360-degree, so you have to introduce another term, the distribution of mx is not one. So mx is related to the medium vector is 0x and is 1x, and whereas x is corresponding phases represented by corresponding phases. So these are the functions actually, different functions over a fundamental cycle. So how these functions are actually spreading over this fundamental cycle, that you have to understand. So if again, if you are again concentrating on the space vector structure, so first of all, if you look at the medium vector mx, this function, if you want to look at, so mx vector actually is for ma, how ma is distributed for different region from 0 to 60-degree. If you start from here, it is 0 to 60-degree, then it is there is no there is no neutral point effect for a phase, and but whereas for b phase there is it is 1. Okay, so m is a function, very simple function, either it will be 0 or it will be 1, and because during this region 0 to this region only b phase is getting affected, so this mb is 1. Similarly, during this region 60-degree to 120-degree, only a phase is getting affected, that's why ma is 1. Like that you can have a table. Okay, this entire 360-degree you can have a distribution table. Okay, similarly, yeah, for the small vectors, you can also have table like this, 0 and 1 table. So for 300 to 60-degree from here to here, basically these are depicted as S naught. Okay, small vectors location is not A, okay, for A phase, is not B for B phase, and is not C for C phase. So these are the location of the vectors, okay. This is for S naught, okay, and they have a distribution, distribution of S naught X over the fundamental cycle, like in this manner. And similarly for other three pairs, which are actually S1, S1A, S1B, and S1C, so they are also distributed in a different manner. This is different from the S naught distribution function. So if you have this knowledge, and this is very you can easily understand, you can easily find out these values, either 0 or 1, to put these values in the table. And then actually then you find a neutral point over the entire fundamental cycle. If you want to see, then you can finally you have IAIB That IAIB can be translated into D and Q axis, okay. So you have the knowledge of these vectors, you have knowledge of these functions, okay. And if you also know this ms1, ms0, and dm, these values, you also know these values. So you can, using these values, using this knowledge, you can easily find out the neutral point, which is expressed in terms of d and q current, okay. D and q current, and this d and q reference is nothing but the space vector voltage reference. So basically, this space vector is along this axis. It is a d-axis, and perpendicular to that is a q-axis. Okay. So with respect to the voltage vector, you can form a d and q-axis, but your current can be different from that d and q-axis. It may be lagging or leading than the voltage. So you want to understand for different current, but for different power factor of current, what will be the implication of neutral point current. So for that, you are actually, everything is comes in terms of d and q, and using this information of md, that is the distribution over fundamental cycle. So with ma, mb, mc, but they got translated into d and q here. So md and mq, and all these got translated into d and q. Similarly, this sa is not a, is not b, and is not c also got translated into is not D and is not Q, and similarly for S1D and S1Q. So everything you are trying to look at from the DQ reference frame instead of looking at ABC reference frame. So the advantage of looking at DQ reference frame is that, so easily you can interpret the power factor, the effect of power factors. Okay. So here you can easily understand this. That comes here. If you split this equation in the matrix form, it is written. But if you split this expression, so this is ID into DM into MD, correct? So this ID is multiplied with this, so that is contributing to the neutral point current, okay. Whereas this IQ is multiplied with this DM into MQ, okay. So so this MD and MQ with multiplied with this ID and IQ, okay, in this manner. So if you look at the effect of this DM and MD, so this for the entire 360-degree fundamental, so for entire fundamental cycle, that means from 0 to 360 degree, if you want to see the effect, how it is changing. So the function is changing like this, okay. Function is changing like this, whereas this DM and MQ, DN and MQ is changing like this, okay. So when you multiply with this ID, okay, then you can see the range of this function is less actually. And whereas when you multiply this part with IQ, this function is already amplified here. When you multiply with even low value of IQ, so that will contribute to the larger of INP. So from this you can draw inferences, okay. So when your current is unity power factor, so then this current will be aligned to d axis, so it will be in phase with the voltage vectors, okay. When it is a perfectly unity power factor load, so your current will be in phase with your voltage vectors, okay. So okay, and so what is happening, so when they are in phase, then this part is be dominating. Okay, for unity power factor, so this IQ can be 0 in unity power factor load. Okay, but as the power factor is drifting away from unity power factor, okay, then this IQ component will increase and ID component will decrease. So when IQ component is increased, then that's a problem, because this itself is big. The DM into MQ, big mean their fluctuation is there. Okay, high fluctuation. When even the little amount of IQ or large amount of IQ is getting multiplied, they get they have a substantial amount of contribution on the neutral point current. Okay, so here is the catch. So from this actually you can actually infer that during the application of medium vectors, okay, the IQ current has more weightage, okay, and cause much more low frequency ripple than the ID component. You can have easily infer from this equation. And in case of small vectors, okay, now this is about the medium voltage vectors, how they are affecting. But in case of small vectors, this is the small vector contribution, right? Sorry, this part is the small vector contribution. But small vector, you have a liberty to control ms1. Because these are the controllable parts. Whereas here there is no controllable part. But here, as I discussed earlier, this ms not and ms1, these are controllable part. That is in your hand. So you have a choice of ms not and ms1. Either you can put them +1 or -1. So you have a two choice. So when it is a +1, so this is the envelope, this is the function is changing in the fundamental way. When you are having a -1, so this is the dotted one is the function, it is changing like this. So you have this whole range. You can, by manipulating whether this value will be either +1 or -1 or in between anywhere. Okay, you want to keep this ms naught, by changing or by controlling this ms naught value, you can put your function anywhere in this region. Okay, so you have a actually control here, you have a control here. So that's why it is saying in case of small vectors, the weightage weighing factors, this ms naught and ms1, these weighing factors can be controlled by adjusting current modulation indexes. So large ID means a large current authority over neutral point current through the manipulation of current modulation indexes of small vectors. Okay. Also, it can be seen that ID, if it is large, then I definitely IQ is less, so fluctuation will be less. So a large ID is always better. Okay. On the other hand, large IQ means a large disturbance from the middle vectors, as I said earlier. So therefore you can conclude that it is much easier to suppress the low frequency ripple in the neutral point when the load has the higher power factor. Okay, definitely. So that is the conclusion. So when you have a low power factor, it is difficult to control because IQ component is getting increased. But whereas it is a unity power factor or close to that, then it is easier to control the neutral point current fluctuation or neutral point voltage fluctuation, and easier to control the neutral point current. By controlling neutral point current, you are actually controlling the neutral point voltage. So that is the beauty. So if you want to inject some particular neutral point current in order to reduce the deviation, that is the idea. Okay, so that idea will be talking here in the next few slides. So basically what I wanted to mean that, so when you have a deviation here due to this current, so you can change your switching strategy such a way, so instead of going this way, the next cycle, the current may go the opposite direction. Okay, without disturbing the volt second balance. Okay, so it may go in the opposite direction. So whatever the change or deviation happened, that can get back to its original position. Okay, so that may again come back near to zero voltage, neutral point come back to zero voltage. Okay, with respect to a virtual zero. Okay, so you can do this actually control on MSO or MS1, so that you can play with the redundant vector locations, okay, so that we have an entire zone to play with. Either it may ranging from +1 to -1, so you can enter by changing this O function. You can also this is the MSO function. Similarly for MS1 function also it can be shown. Here only is shown for MSO function. This is with respect to D, and this is with respect to Q. So here you have seen that D has a more range to play with, whereas the Q has a lower range to play with. That's why if you have a large ID, so it is easy to control. Okay, easy to control the NP current, which will be required to change the which is required to nullify the effect of the neutral point voltage deviation. Okay, so neutral point balancing of the DC link capacitor voltage for 3-level NPC VSI is possible for balanced linear load conditions. Okay, now we'll be looking at into some other effects. But as long as we are talking about balanced load, linear load conditions, the GQ reference frame we are changing, all even the current ID and IQ. So all these are actually in the condition of balanced linear load conditions. So you can easily do that analysis. However, due to flow of neutral current, a low frequency ripple comes on the neutral voltage. This is at the 3 times of the fundamental frequency. So it is observed that the ripples actually are coming, that is 3 times, and also it can be observed here. If you look at one fundamental cycle, the frequency here is repeating in three times of the fundamental frequency of this waveform is 3 times more than the fundamental cycle. So here also and here also we can see they have a clear indication that why the neutral point is actually frequency low frequency is coming 3 times of the fundamental. So that is what the 3 times of the fundamental frequency is coming. So mainly at high modulation index and low power factor. So this low power factor we have already analyzed why it is coming more on low power factor, but this is also coming at high modulation index as well. Why it is coming around high modulation index more and more? Because you don't have control of the of a ms naught and ms1, because ms naught and ms1 are related to small vectors. So when you are going to higher modulation index, your applicable time on the time or duty ratio for the small vectors are getting reduced for the small vectors. Okay, for the small vectors, the duty ratio ds naught or ds1, that is also getting reduced. When ds1 and ds2 is getting reduced, so because that is also getting multiplied with this ms naught. Okay, so cannot play much because if your dso is more, then you can have better role to play. Okay, so you can correct more. So that is what actually is said here. So under non-ideal condition, NP voltage. So if you just I pointed out in yesterday's lecture that if you do the simulation, mostly you will be doing the ideal condition of the power circuit. So you may not observe this neutral point fluctuation, but if you actually do this study under non-ideal condition, and in practical case and in hardware case, it is actually so you cannot make everything ideal, right? So there will be imbalance between the top switch and bottom switch. There must be some nonlinear effect in the loads. There will be dead time effects and all. So all these imperfection, and sometimes there will be some little bit of transient in the current. The due to transient mean it leads to the it actually give rise to the little bit of imbalance, temporary imbalance to the loading condition. Okay, so all these give rise to a non-ideal condition. So that will make sure that your neutral point might make sure may shift neutral point may shift from the center potential of the DC link. So this is the problem. This is stated, the problem is stated and is analyzed and understood, and what are the typical conditions you may face more challenge. Okay, so the typical condition is a low power factor and high modulation indexes. So then why you require neutral point balancing? So for a very simple reason, that if you don't put neutral point balancing, then one capacitor will be having more voltage than the other one. So one switch, the top switch or the bottom switch, will get excessive voltage trace, so unequal voltage trace, and sometimes it may cross its the limit its rating. Suppose you have chosen a device with some margin, it is the application of total VDC, so we'll be designing your switches as VDC by 2 and VDC by 2. Okay, the middle two switches, but basically, or all the switches, you can look at this circuit. See, all these switches are rated at VDC by 2. Okay, but because one of the capacitor voltage got much higher than VDC by 2, so they will be sharing more than VDC by 2, and if the rating of these switches is crossed, then these switches might fail. Okay, so that is also another issue. That's why we require neutral point balancing. So we avoid excessive voltage trace across the switching device. And when the floating NP, so basically NP point potential is floating, it is changing, not fixed to a zero value. So it varies from the center potential of the DC link voltage. Okay. And to eliminate the low frequency harmonic distortion. So not only this issue, but also this fluctuation in the neutral point, that is getting in the output voltage also, it is getting reflected, or the pole voltage, or in the phase voltage, or line to line voltage, these fluctuations also getting reflected. Okay, so then that output voltage also having those components of those frequency components, and so this is causing a harmonic distortion at the output voltage. So these are the constants. That's why you require to keep the neutral point voltage balancing. But if you look at is from the previous study, if you try to analyze the if you change the power factor, here another figure is shown. So here if you change the power factor, and the modulation index in the y-axis, and the x-axis is the power factor you are changing. So middle point is a zero power factor, and this area, the hatched area, is the good area. Actually, this area you would like to stay. Okay, because in this hatched area, if you fall in this hatched area, then you are happy because you are able to control the neutral point. And if you're outside this hatched area, then then you are in danger because you are not able to control the neutral point voltage. So if you study the limits, okay, so that limits will be depicted by these lines, okay, which is showing the boundary of this hatched area. So the region where low frequency ripple can be suppressed, so this inside this hatched area, low frequency ripple can be suppressed. So when you are actually at zero power factor, or unity power factor, zero power factor angle, that means unity power factor, so you can go all the way very close to modulation index 1. Okay, without much problem of neutral point voltage balancing. But as you drift away from zero power factor angle, so your power factor is decreasing. So then at 90 degree, you can see this is the this is the low range actually, because the 90 degrees is the worst case, both side of plus 90 and minus 90. So you will be hitting at the low extreme zone actually. So because if you trying to increase the modulation index more than probably zero point 0.6, then you get more and more problem of the neutral point balancing at minus 90 degree. Similarly for plus 90 degree also, similar situation, you will get it. Okay, so those are actually till now we are talking about a scenario where you will where your load is actually a balanced load, okay, linear balanced load. Now your load cannot be always balanced. There must can be some imbalance in the load. There maybe have some nonlinear effect in the loads, because some loads are switching in nature. Suppose you are using a switch in the load, semiconductor switch, so that causes the nonlinearity in the load current. Okay, so that was studied in this particular paper. So if you can refer also this paper. So effect of unbalance. So first of all, there are two different classification of this imbalance, right? So one is that linear imbalance. So linear imbalance is not that fatal, is not so much dangerous, but still it is a concern, but it is not fatal than with respect to nonlinear kind of load. So a linear load, but it can be unbalanced load, correct? So this is the kind of example in the right hand side. If you look at, so IA, IB, and IC, they are sinusoidal currents. They are smooth waveform of the current, but the amplitudes are different. Okay, the IC amplitude is much lesser than IB and IA amplitude. So this is regarded as a unbalanced, but is still regarded as linear load. Okay, but the left hand side is a more ideal condition, and not only ideal condition, you may face this condition quite often. So most of the loads are balanced. So but these are not only balanced load but also a linear load, smoothly even changing. So this is the most happy condition you can get. So here still you are getting a fluctuation in the neutral point voltage depicted by VC1. Okay, this is the neutral point voltage. So this is a voltage, output voltage and output currents, and this is the neutral point voltage fluctuation. The three times of the fundamental frequency you will be observing here. Okay, and obviously you can easily understand this may be working little bit of. You can look at the current IA and IA, and this is the phase voltage. Okay, this is the phase voltage. So IA and sorry, line voltage, I'm sorry, is a line voltage. So this IA line voltage, if you look at, and there is a angle. So basically it is not it is not actually unity power factor. It is actually much away from unity power factor, so low power factor operation. Definitely you can observe low power factor operation, some kind of fluctuation, okay, in the neutral point voltage. Okay, so that's why you are observing this. And also it is a maybe operated at quite high modulation index, so this fluctuation can be more perceptible. Okay, and but at the end of the day you may not lose the stability, although they are fluctuating. So in a fundamental sense they are trying to balance, but they are fluctuating. So this can be cause a concern in your power quality, right? At the output of the voltage may get disturbed because of that. Yeah, as you can see, some small disturbances in the line to line voltage as well, although this is not very high degree of fluctuation, but still this fluctuation may cause some fluctuation in the line to line voltage. So this is actually a linear load and balanced load. But if you look at the linear and unbalanced load, so the fluctuations got increased in the VC. Okay, the fluctuations got increased in the VC. So there are more amount of fluctuations you can observe. Okay, so definitely this plays a significant role, the kind of load you are providing with. So not only the power factor, but also if there is a unbalance in the load, so that plays a role in the fluctuation of the neutral point voltage. And that is what it studied in this particular literature. So now, if you want to look at the nonlinear effects of the loads, so this is much more dangerous. So that might cause instability. Still, till now, we are not looking, we are not observing any instability. So that means, although it is fluctuating, it is not getting diverged and it not going away from each other. Okay, the two voltage of VC1 and VC2. Okay, they are not drifting away from each other. But if you have a sufficient amount of nonlinear effect in the load, so that might cause a severe problem of stability issues in the neutral point. So this is the effect in the first figure. You can see when you have a second harmonic components, when you have a fourth harmonic component, and fifth harmonic, seventh harmonic, eighth harmonic, and tenth harmonic, and so on, so and so on. So but this particular observation talks about the effect of individual harmonics. Okay, so you can easily observe that the even harmonics are much more dangerous if it is present in the nonlinear loading condition, but whereas the odd harmonics are not that much detrimental, but obviously they will cause some concern, but it will not cause any instability as such. But whereas the fourth harmonic is causing much instability, as well as second harmonics. But eighth harmonic also can cause instability, but it is not in a that faster manner it is not going away. But 10th harmonic was almost stable. It is not causing much problem. So, but all these results are shown without taking much action on the neutral point potential, not, because you are not actively trying to control the neutral point potential. So this might happen. But if you would like to try to control the neutral point voltage by changing all those MSO, MS naught and MS1 and different control techniques, PWM control techniques, then these effects will be improved definitely. But this is the observation, so which that might cause more into the neutral point, and which is causing more effect on the neutral point. So this is a kind of observation, okay. And also if you this is just another depiction of actually how this second harmonic can play a detrimental role, because if you change the magnitude of the second harmonic, okay, so in the nonlinear load, and as the phase angle power factors is changing, okay, so this is the limiting condition, okay, this is the maximum tolerable amplitude of the second harmonic magnitude which you can tolerate, okay. Beyond that range your instability problem may come. So you are actually quite okay with unity power factor. You can survive with 84% of the, okay, so 0.84 modulation index, and still you can survive almost near to 110% of the uh, second harmonic component with respect to the fundamental component, okay. But when you are away from zero, so your limiting values are actually dipping down. That means you are less tolerant of second harmonic, you are less immune to second harmonic as you are drifting away from the zero phase angle. Okay, that is expected, that was we were expecting that will happen. So okay, so these are the very important observations. So now let us try to look at some of the solutions, so how people used to do. So these solutions, again taken from some reference, the reference is cited here, but they're classified into three different categories, where passive control, hysteresis control, and active control. But passive control is just not used. Basically this is a inactive way of control. It is just you are giving a times they are equal to the two redundant vectors of small vectors, equal times you are providing. So it is not actively controlled. Whereas this hysteresis control and active control, they are all part of the active control. Basically here the white they are called active controls, because you are actually sensing the neutral point unbalance using the voltage sensors. And also you need to know the knowledge of the current, okay, particularly the current direction you need to know, so that you can play, actually you can manipulate these values of these per ms naught and ms1, and based on these, but these sensing values, okay, measured values, and you can take appropriate action on your neutral point voltage deviation. So there are two different ways of doing the things. One is hysteresis control. This is kind of on-off control, and this is the active control. So basically, hysteresis control, you give the entire time on particular redundant vectors, but whereas in active control you don't give the entire time to a particular redundant vectors. You split the time of two redundant vectors, and you are giving those time in a particular switching cycle. Okay, so anyway, so anyway in passive control it is not immune to actually sometimes it may fail. Passive control, you cannot rely on passive control, because sometimes some large transient comes, and then you, from there on you may not able to come back to the stability. But in case of feedback control, this is called feedback control. Both can be classified, hysteresis and active control can be classified as feedback control. So they can be easily controlled, right? So these are the actually 3D plots showing actually normalized NP change, how much fluctuation of the NP voltage. If it is flat, that means it's no NP voltage balancing, there is no rise in NP voltage. But as it goes high and high and rising with these blocks, then that means there is more NP voltage balancing, and that is in the y-axis, in the z-axis. And this x and y-axis, one axis is shown power factor, another axis is shown modulation index. But you can easily understand that feedback and in neutral point control is having much control on the neutral point balancing. because it is a lot of flat portions, right? So flat portions means zero deviation. Okay, so there are other techniques reported in the literature. One is the nearest three vectors and symmetrical modulation. So there are two different techniques: nearest three vectors and symmetrical modulations. So here, if you simply compare between these two, this is first one is nearest three vectors, and second one is symmetrical modulation. Actually, what is this? Actually, in nearest three vectors, you are switching the way you are trying to switch, because here number of steps sometimes it become two. So when you are switching the three nearest vectors, in order to have a volt second balance, so the way you are switching, that is called switching pattern. And this switching pattern under these nearest three vectors is like this: for different zones, for 1 2 3 4, and so it's basically it's 1 1, this is the 2, and this is the 3, and this is the 4. These are the zones. Whereas the symmetrical modulations, and depending on different zone, and again here it is getting categorized. Zone 2 again getting split into two different zones, and zone 4 also getting split into two different zone. So you are getting a different pattern of the switching. The switching pattern will be different than the NTV scheme. So here you will get more number of steps overall, but here you will get overall less number of steps, but your switching frequency may not remain constant. Whereas in symmetrical modulation, one advantage is that your switching frequency remain constant because of this symmetrical switching pattern. So, but if you look at if you compare in terms of NP voltage balancing capability, so NTB has better neutral point voltage capability, because you have more flat area. You can see here, as more flat area, more better is the neutral point balancing capability. Whereas symmetrical modulation is also very good, but not that good compared to NTB. In a little bit more wavy in nature. Here, little bit more heights you are getting, and little less flat portion you are observing here. So that depicts that this NTB sometimes, although have more different and variable switching frequency, but it has better neutral point controlling capability. And you can see from this figure also, this higher the change BC1 and BC2, the difference between these two is very small. But whereas this BC1 and BC2 for symmetrical modulation, sometimes it go little larger in some places, okay, depending on the power factor and modulation index. Okay, so move on to the next another solution. So there are another solution available in the literature as depicted here in this reference. This non nearest vector strategy. Since non nearest vector strategy is nothing but the virtual space vector PWM technique. So here what you do, you are instead of relying upon the vector physical vector location, you are actually you are creating a vector locations by splitting, by time sharing of two existing vectors in the space vector structure. So when you are time sharing two existing vectors, then you are getting in effect a newer vector location. Okay, again that is also in a whole second balancing methods, but in effect you are increasing the number of switchings. Okay, because when you are trying to get a virtual vectors from derived from the existing vectors, so you have to do lot of more switching. So that is anyway is possible, it is, or anyway it is, we have to sacrifice. But the advantage of these virtual vectors is that for each every vector location is itself is sufficient to eliminate the neutral point voltage. So suppose if you was getting a vector splitting this S1 vector location, and it's a two redundancy, so you were splitting exactly half and half, so contribution of your neutral point will be nullified to zero. Similarly, here in the midpoint, this is also location of a virtual vector. So here you get this VIA and IB and IC. So when you add them together, so IA plus IB plus IC will become zero. So anyway, these long vectors, you need not to do anything. They are not contributing to any neutral point. So they are happy to retain the long vectors as it is. But whereas the medium vectors and small vectors, they are constructing in a new way. and then they are actually trying to get different zone and different switching scheme using these virtual vectors. So this is something different way of switching, but that leads to more number of switching. So if you look at the disadvantage of the scheme, but some advantage obviously is there, but some disadvantage is also there. I am just listing down the disadvantages more. So about one third more switching transient than uh, NV strategy, the nearest vector strategy, or the same switching frequency. So if you look at more number of switching in the line to line voltage, this line to line voltage get more distorted than the usual output of the line to line voltage of other strategy. So, and neutral point voltage balancing is achieved at the expense of increased output voltage switching distortion, as you can see, and also the switching number of switchings also getting increased, causing more amount of switching losses. Okay, so this is what, and this is the probably the last one, but this is most maybe sometimes most efficient one. So this is called hybrid repeatable strategy, where they are actually using the previous two strategy is S3V, and that is the S3V is nothing but NTV strategy, nearest three vector strategy, where you can see the load current itself is actually not balanced. Okay, and they are having some nonlinear elements also involved, so you are able to get at least satisfactorily some amount of balancing is possible using this S3V. Whereas if you switch over to symmetrical switching, so symmetrical strategy, symmetrical mean we have discussed this two different, this is NTV and this is symmetrical modulation. So basically they are switching between these two NTV and symmetrical modulations, but symmetrical modulation not able to retain the neutral point voltage as good as this previous one. So but it will not be unstable, but it will be fluctuating like this. But when you switch over to a hybrid scheme as depicted in this flowchart, so hybrid scheme are able to switch between these two schemes, is NTV and symmetrical. So they are able to switch as and when required. They are able to switch between these two modes depending on this particular condition. This seven does seven hold. If it is yes, it will go to nearest vector. Otherwise, it will go to non-nearest vector. This is virtual. It's called virtual vector strategy. So they are mixing these two strategy. Virtual vector mean we have just talked about this virtual vector. Basically, they are mixing about these two strategy. Then they are getting much better waveform. But what is the seven condition that is actually shown in this particular reference? I am not skipping this further explanation. What is this condition, because it will complicate the thing. But using that particular condition, either you can switch to NV strategy or you can switch to non-NV strategy, and you can get hybrid solution, which will be giving you much better of better neutral point voltage balancing capability for the same loading condition. Your loading condition is not changed. Okay, it has definitely, it has some control complexities involved. Sometimes it may not be so much useful because it having a lot of complex control complexities. But sometimes if you are very much particular about controlling the neutral point voltage very tightly, then this can be used. Okay, and I'll be concluding it very quickly. So here the intention of showing this is not sea level. Okay, here actually this is the one of the work has been done in our lab. So basically I'm demonstrating that particular circuit here and the neutral point voltage associated to the circuit, how we are solving the neutral point voltage balancing capability, and neutral point voltage issues, how we are solving. So basically, this is the five level strategy. So earlier we are talking about three level. Now this is giving you a little bit of different flavor, because in this particular five level, you have two role to play. You have to control PWM control has two role to play. One role is to balance this flying capacitors. Another is the same time it has to balance this neutral point capacitors. Okay, DC link capacitors. You need to deal with both these capacitor balancing technique. So that calls for a special strategy, and so you can, from the switching table you can easily understand that for getting different voltage levels. And so there are five levels: one, two, three, four, and five. And in this, in between this particular level and this particular level, you have two redundancies, two different circuit paths for the same voltage output. So that will lead to actually either if you look at the status of the FC, one will be charging, another will be discharging for the same voltage output. If you use this redundancy, then you will get different effect on the FC. So you basically switch between these two, or switch between these two when your modulus, your wave reference is passing through this zone. So that you can have a balanced voltage at the FC. But what is the problem when you are trying to control this FC voltage by changing over this one or two, or the same voltage level, but one is 1 1 and 1 2. So your first one is not having an effect on the neutral point, and but second one has an effect on the neutral points. So that creates a problem in the neutral point voltage balancing. Suppose so one is not having an effect, another having effect on the neutral point. So you need to consider a ratio. So the time, when, how much time you are actually giving for this particular redundancies, because this is an effect on the neutral point, and how much time you are giving for the other redundancy. So the total time you are giving for this level, that is comes in the denominator, and the time you are giving for this particular level comes in the numerator. That is depicted as Rx as a reference. And by changing this Rx online, so this is a complicated, little bit complicated for you for the time being to understand. But we can change the Rx dynamically in the online, but just to control the neutral point as we are controlling the flying capacitor, because there is a dependency between flying capacitor control and the neutral point capacitor control. So this is just a small demonstration, and this is the some results. uh, so for the same study, so basically dynamically changing ratios, and whereas there is no dynamically changing ratio, the fixed time ratio is used. So compared to the fixed time ratio, the dynamic time ratio is performing much better with in some certain conditions, like particularly for low power factor conditions. Okay, so that is the demonstration is shown. If you are further interested, you can refer this particular paper. Okay, so this is what is all about. So this is the kind of research is going on, not only for 3 level, 5 level NPC and TNPC structure. Also, people are coming and doing a lot of contributions. That's all from my side. I try to conclude by saying so, and hopefully you might feel interested to ask few questions. Okay, so now it's open to you. If you have any questions, please let me know in the chat box. I'm sorry for some of the confusion, because it is not very much easy to understand at the first go, and that is not so easy for 1.5 hours time to understand each and everything. But you know that you have all the references, and if you are interested, you can further investigate and clarify some of the doubts. But for the time being, if you have any queries, definitely I will try to explain, and that will be easy for you to clarify those doubts very quickly. Otherwise, it will be difficult to know. I'm just waiting for your queries. If you have, please let me know. Or you can raise your hand, and so that I can unmute you, and you can also say something. You can also unmute. You can unmute yourself if you would like to say something. You can unmute yourself now. Yeah, from your end you can unmute, and if you want to say something, you can please ask few questions. Yes, yeah, sure. I will share the lecture video. I'll first the recording of the lecture videos will be shared with you, so that will be for your future references. Of course, I'll share that. But right now we have probably 5 more minutes we can spend. If you have any quick queries, it will be easy for you to follow, right? If you have clarify those queries, then in future it will be easy for you. Or also you can write some of your doubts in the email provided in this slide. So right now you can unmute from your end if you wish. You can unmute and come forward to say something. So if there is no further queries, just I would like to know that there will be, as usual, the afternoon session will start 2:20 p.m. and then onwards, all the three more succeeding days will be coming, and same similar manner, morning session and afternoon session you should attend by other teachers. So this was my last lecture as long as my lecture is concerned, but there will be other resourceful persons available, and they will be delivering their respective topic. They will be talking about those topics in a more elaborate manner, and so that it will be very helpful for your research purpose in future. So please try to join each one of this session, and definitely will get benefited out of this session. Okay, thank you from my side. Still I'll be waiting for a few more minutes if you have some queries.